All right, welcome to the fourth and final part of this little series. So what we're going to do is look at questions 31 through 40 on this. So we'll start with question 31. For students in one college, the expected value for the number of siblings is 3. Consider the law of large numbers. What is the following statement is a reasonable conclusion? If a student is selected at random, the most likely number of siblings is 3, and that's the large number says it on average. So it's not good, but let's see if there's a better option. That's not a good conclusion. If 100 students are selected at random, the average number of siblings for the 100 students will be close to 3. That actually makes a little bit more sense, especially with the law of large numbers. I like that one so far. If 4 students are selected at random, the average number of siblings for 4 students will be 3. I like B better because of the law of large numbers says the more numbers you collect, the closer to the average you'll be. If a student is selected at random and has 6 siblings, the next student selected will have no siblings. And once again, goes back to 1 student in random, 4 students at random, 1 student at random. You want large numbers, and so that's really what we're looking for is those large numbers. Question 32. If you want to calculate the total number of outcomes, where does some of the items from a set, each item may be selected once. The order of the arrangement does matter. Which of the following formulas would you use? Well, since order matters, we want a permutation. If order didn't matter, we would look at combinations in the other options. So permutations are for when order does matter. All right, next option. We want to calculate the total number of outcomes where some of the items are selected from a set, and each item may be selected once. The order does not matter. Okay, so it can be selected once and order doesn't matter. So since we're selecting once and order doesn't matter, it's a combination. If you want to calculate the total number of outcomes where each item may be selected over and over, so now we have repetition, okay, you would want to use the following formula. So since we have repetition, and we're going to select, each item may be selected over and over, we're going to replace it and then keep selecting it, so it's just going to be the number of times raised to how many we want. Alright, so number 35. How many 6-character passwords consisting of lowercase letters and numbers are possible and the last character must be a number? Okay, so are we allowed to have repetition in this case? 6-character passwords consisting of the lowercase letter, and number. So there's 26 lowercase letters, and there are 10 numbers, 0 through 9. Okay, the last one must be a number, so the last one has to be that 10. Okay, and so repetition is allowed in this one. So I'm going to say 36 options for the first one, and we're doing 6-character password. 36 options for the second, for the third, for the fourth, for the fifth, and the last one, the 6th one, has to be 10 because it has to be a number. So that's going to be the number. So we come down here, and I'm just going to go 36 raised to the power of 5, and then multiply that by 10. So looking across here, C happens to be the correct answer on 35. Imagine that you're judging a Miss Junior pageant and you need to select 3 winners, a queen, first runner-up, and second runner-up. Okay, so this one order matters because you can't be, it would be a different order if you had a different queen. From 10 final candidates. Okay, now in this case, let's say they all have equal probability, so we're just looking at the number of permutations in this case because of order mattering. So we have 10 up, we want to have down here, let's see, there are 10 final candidates, permutation, and we only want 3 winners, so I'll put a 3. So now what we need to do is 10 factorial, or the n factorial, over n minus r, or 10 minus 3 factorial. So this is equal to 10 factorial divided by 7 factorial. And so that's 10 times 9 times 8 times 7 factorial divided by 7 factorial. And what we're going to do is we're going to cancel out those 7 factorials. And so we're left with 10 times 9 times 8, or 720. So D, 720 ways are the correct answer. And that was 36, so let's do 37. I'm sorry, that was, yeah, problem 36 was right. All right, 37. There are 13 members on a board of directors. They must form a subcommittee of 4 members. Now, in this case, order doesn't matter. Sounds like how many different subcommittees are possible. Order doesn't matter, so we're looking for a combination. So there are 13 members, so our n is 13. We're looking for a combination of 4 members. So let's go ahead and do this calculation. That means we have 13 factorial divided by 13 minus 4 factorial times 4 factorial. Or 13 factorial divided by 9 factorial, 4 factorial. In this case, 13 times 12 times 11 times 10 times 9 factorial. Notice that 9 factorial will cancel out with the 9 factorial at the bottom. So I'm left with 4 times 3 times 2. The 9 factorials cancel out. And I'll just do that calculation. 13 times 12 times 11 times 10. And we'll divide that by 4, divide that by 3, divide that by 2. So 715 is the number of different subcommittees we can have. Okay. 38. There are 5 women running in a race. The person guesses randomly first place, second place, and third place winners. What's the probability that they will guess all the winners correctly? Order matters in this case. First, second, third is a placement, so order matters. And we have 5 runners. So we have 5 total, and we're going to do permutation because order matters. And we're going to select 3. So that's 5 factorial divided by 5 minus 3 factorial, or 5 factorial divided by 2 factorial, which happens to be 5 times 4 times 3 times 2 factorial, divided by the 2 factorial. Those cancel out. So I'm left with 5 times 4 times 3, which happens to be 60. Okay? Now, that's how many options there are. Okay, looking over here, we need to look for the probability. There's only one way to get that. So there's 60 possible combinations. Now, the first, second, third, if you get that right on, there's only one way to guess that. So 1 out of 60 would be the probability to guess that, or C. Right, 39. If the rules of a lottery game Powerball require participants to choose 5 unique numbers ranging from 1 to 59 in the order along with 1 Powerball which ranged from 1 to 35, what is the probability of winning the jackpot under those game rules? Okay, so there's only one way to win, and so we need to find out all the possibilities. In this one, okay, we're going to choose 5 unique numbers. So unique numbers meaning, so this was going to be a combination of those first 5 numbers. Because in this case, order really doesn't matter, but they're 5 unique numbers. Okay. Now, if they said, you know, your first number has to be the same as the second number, that would be different. But this one, you just have to have the 5 numbers in order. So let's look at this. We want to, but they have to be unique. Okay, so they have to be different. So we have 59 options. And we're going to do a combination with 5 of those numbers. So therefore, we have 59 factorial divided by 5 factorial and 59 minus 5 factorial. And 59 factorial divided by 54 factorial and 5 factorial, which would equal 59 times 58 times 57 times 56 times 55, and notice the remainder on that will be 54 factorial, which I can cancel out with the bottom one. And then I divide that by 5 times 4 times 3 times 2 times 1. So 59 times 58 times 57 times 56 times 55. We'll divide that by 5, 4, 3, 2. So now this is this number right here is not complete. That 5 million, we still have to multiply this by the number of possibilities of the last one. And in this case, there are 35 options for that. So I'm going to multiply this by 35 options for that Powerball. Multiply that by 35. And now I get 175,223,510. So it's 175. Now there's only one way to win this whole jackpot. So we'll put 1 over that. And that is our probability. So in this case, it will be C. And the last problem, evaluate the following ratio by taking advantage of the definition of factorials. And so this actually is quite easy from what I've been showing you. 693 factorial divided by 690 factorial. So we'll go 693 times 692 times 691, and then that's times 690 factorial, and all divided by 690 factorial. Those cancel out, and I'm left with let's clear this out, 693 times 692 times 691, or that number right there. So B happens to be the correct answer by taking advantage of that ratio. And that's finishes up exam 3. If you have any further questions, please don't hesitate to email me or call me. And good luck on your test.